Resume recording. All right, so we had left off with cyclic voltammetry. And cyclic voltammetry is probably the technique that you're going to see the most if you go into chemical research. So this is a very research-heavy technique. You do see it in some non-research applications, but like if you're going to go work in a lab that's going to build a new material, or you want to look at electron transfer or something like that, you're probably going to be doing some cyclic voltammetry to characterize your material that you make for your compound. And so remember, the way it works is that we have one of those 3 electrode cells, and between the reference and the working electrode, we're going to slowly change our potential that is applied between them. All right, so we're going to ramp up our potential, and then we're going to turn it backwards and go the other way. And as we do that, we observe the current that flows between the working and the counter electrode. And so nothing's going to happen for a while, right? So nothing's going to happen until we reach some critical point, and then our redox reaction can start to occur. When that happens, electrons go from or hop on or off of the electrode onto our molecule. Because I'm now moving charge around, that's a measurable current, so our current starts to go up, right? And it's going to go kind of in a V equals IR kind of way, right? Until we reach here, when we start to deplete stuff, right? We start to run out of material at the electrode surface. And then it's going to be like, oh, no, I've got a decrease in concentration. So this decay is going to be, the current is going to drop off until we reach this switching voltage. This here is our switching voltage. So our switching voltage here was minus 1.5 volts. And then it's going to regenerate, if it's a reversible reaction, our reactants. So it's going to take our products and convert them back into the reactants. So we got a lot of stuff at that surface that is the products that we're now converting back into reactants, until those guys reach some peak and they start to run out, and then we start depleting and running out of those products that we're converting back into reactants. And so we're changing our voltage and we're observing our current. And if we get a nice symmetric looking duct like this, and then we have a nice reversible reaction. So we have a reversible reaction where it is fast enough to maintain equilibrium concentrations of the reactants and the products. And the peak anodic and peak cathodic currents have equal magnitudes, right? So this guy between there and there is the same height as between, if you draw a line on this part here and here. Okay. The separation between EPA, our peak anodic current, and our peak cathodic current, right, halfway in between them is our E1 half. And the magnitude of that separation is related to 2.2 RT over N times F, right? So 57.0 divided by N, right? Because R is a constant, temperature at 25 degrees is constant, N, Faraday is constant, is a constant. So all these things get rolled up, and basically it's saying that you can, if you look at the separation between those two peaks, figure out how many electrons are involved in that redox process, which is really useful to know. Right? The halfway potential, or E1 half, lies halfway between those two peak potentials. Remember that E1 half is related to the E naught, right? The guy that you would find on the table of reduction potentials, just adjusted a little bit because you're now doing that relative to the reference electrode. So it's going to give you your E naught values. You're going to figure out how many electrons are involved in that process. The shape of this curve is going to give you information about whether you've got a reversible or a non-reversible reaction. Sometimes you'll get multiple peaks, and we'll talk about that. But there's a lot of things you can learn out of this. Right? The increased separation and broadening of the cathodic peaks and anodic peaks occur in an irreversible reaction that just aren't fast enough to maintain equilibrium concentrations at the electrode, or you form a product that's not going to be there, right? So if you form a gas, right, your gas bubbles away, you're not going to get that gas back at the electrode. or if you form a precipitate and it falls down, or some things just have a really high activation barrier, energy activation barrier in that reverse direction, and you just can't get it to go back the other way until you really drop that voltage and apply a significant overpotential. For a reverse reaction, the peak current of the forward sweep of the first cycle is going to be proportional to the concentration of the analyte and the square root of the sweep rate. All right, so your current here is going to be proportional to your concentration, so you can get some quantitative information out of it. And if you want to increase the height of that peak, right, if you want to get a bigger, excuse me, a bigger peak height, right? So let's say I've got two, guess you just learned how to draw on his slides, right? So if I've got two voltage profiles, right? I got a slow one that's really slow, and then I've got another one where I'm going to go fast. Same magnitude, but in one case I'm going to make it that I'm going to switch the knob real fast. Right? You would think, right, just kind of on the gut intuitive level, that slowly changing that thing would be better. Right? But what we see in the actual cyclic voltammogram is that we might get a little one for this guy, whereas in this one we would get a much bigger response. And when you think about what it means to be current, right? So current is the flow of charge with respect to time. And if you were switching that knob back and forth really fast, what are you doing to that time base? Well, you're really accelerating that time base and you're making it go faster, right? So as you switch that voltage rate, that's this guy, this is our sweep rate. Okay. Our sweep rate is going to affect how tall these guys are. So sometimes if you are running an experiment and you can just barely see your peak, sometimes you can increase that by making your reaction go faster. Sometimes that will have other effects, like you might start to get it a little bit less reversible, right? So you might end up with instrumental lag. So if you go really, really fast, you run the risk of making your peak separations bigger than they actually are. So you might end up screwing up your information about N. The other thing that's in here, so we got this current, right? So how high does it go, right? One of the weird things is that you measure it from this little line here, right? So this is the height, not this. If you were doing something that's semi-quantitative, you can probably do base to peak height the whole time, and it's probably not going to matter. The great part. The other things that go into it are obviously the number of electrons, right? If you've got a 2-electron process, right? So I've got, here's my thing, and 2 electrons come off of this, right? And versus this one where only 1 comes off, then, right, this guy's going to have twice the amount of charge happening per reaction cycle, so it's going to have more current, right? Because Q is equal to I times T, right? So your current is going to be proportional to charges per second. This guy here just rolls up some R's and some T's and some ln to log E stuff. A is going to be the area, right? So the area of that electrode is going to matter. If you've got more surface area available to you, you've got more ability for things to access that surface, and more things can undergo that redox process at the electrode surface. And so your current is going to be proportional to some constant, the number of electrons that you use, the area of your electrode, the concentration, how quickly you zip your potential, and then D1/2, this is the diffusion coefficient. So sometimes if you want to look at a molecule and you want to know something about how it behaves in solution, that diffusion coefficient is important because that's going to be related to things like what's the charge on the molecule, how big is it? You know, it's basically saying how fast that molecule can move when it takes this random path, random diffusion path through a solution. The faster the sweep rate, the greater the peak current, as long as it is fast enough and reversible. So here's two separate experiments. We've got a reversible one and a non-reversible one. The first one is 1 millimolar oxygen and acetonitrile with 0.1 molar C2H5 and ClO electrolyte, and B is 0.06 millimolar 2-nitropropane and acetonitrile with C2H5 and plus ClO electrolyte. And you're doing the same scan rate. One of them, curves A and B would naturally lie over each other in figure 17. They've been artificially displaced to vertically to enable you to see them better. So they're just, one's reversible and one's not. So you can simulate one of these guys. And this is a simulated cyclic electric voltammogram for a planar electrode in a solution of iron hexacyanide. So you got a potential sweep that you're going from plus 0.75 to minus 0.25 volts. So notice that this guy is potential down here versus the saturated calomel electrode, and Y is current. Right? So our little triangle wave, that is potential as a function of time. This guy is current as a function of potential. It's kind of cool. You could probably visualize that in like a three-dimensional graph where you're actually combining the two things. It's kind of neat to visualize. But the reverse sweep from points D to G oxidizes the iron back. So you're going from one place, you're going from A to B. You're undergoing the reduction from the undergoing the reduction from the 3+ iron to the 2+ iron, and then from D to E, you're starting to do the reverse of that. You're oxidizing from the 2+ back to the 3+ form. And so if you look at the concentration gradients, that is saying like from the distance from the electrode, what chemical species do I have as we start to approach that electrode surface? Out in points D, C, and B, right up in here on this first part, you mostly have this iron 2+ form in the bulk solution, right? And then it's going to decrease as you get towards the surface. Okay? If you were looking at points E, F, and G, so E, F, and G, which is where we're starting to deplete that product formation, you're looking at a more complex profile for your 3+ form and for your 2+ form. And so in the beginning, things are usually nice and neat and organized. So when you do the back sweep, things get a little bit more complicated because you're not starting out with just pure product or the pure 2+ form in there. So it's going to be a little bit more complicated. And this is just showing what that looks like for that. Do I expect you to know how to reproduce this? Just that in the beginning, practically speaking, it means that this first wave that you see is usually a lot neater and tidier and more well-behaved than this reverse one. Here is the reduction of Buckminsterfullerene, whose initials are BMF. So it is a pretty cool molecule. What you see in the reduction of BMF is 1, 2, 3, 4, 5, 6, 7 different peaks. So you're going to have, or 6 different waves, 6 different reduction waves. And if we took that and we did a polarogram, and we'll talk about polarography in a second, we're going to say there's 6 different waves as you start to subsequently reduce this further and further and further. So if you've got the the ability, I was going to say potential, if you've got the ability to undergo more than one redox step, sometimes you can see that. So for example, we could do one with iron where we go from iron 3 to iron 2, and then from 2 down to 0. Here on this fullerene, right, we've got the ability to pull off subsequent electrons multiple times, right? Because it's a nice big molecule. You can pull off a lot of electrons from that. So in polarography, what distinguishes polarography is primarily the use of this dropping mercury electrode. The DME is kind of what makes polarography polarography. In polarography, you're going to keep your solution absolutely still. So this means you can't have people walking in and out of your labs. You don't want to put it in a place with a drafty window. You've got to keep this sucker really, really, really still. And what happens is that diffusion alone controls the limiting currents. So because there's no stirring, there's no agitation of that surface, the thing that limits your peak is going to be coming just from that D term, just from that diffusion. We're going to use very, very, very small currents, or we're going to get very, very small currents out of this. So we're talking like microamps. Right? So you need some pretty sensitive equipment to do this. It makes it hard to work with. So I've tried to do this, and it was a giant. It was not a good day in the lab, or a good couple of days in the lab. Just getting the equipment set up and then making all of your connections and having it hooked up to your voltmeter or your potentiostat in a way that it's going to make it stable reading is also really difficult. Your current has fluctuations as individual mercury drops fall and refresh the surface of the electrode. So your electrode surface is literally a teeny tiny ball of mercury at the end of a capillary. And so it's going to grow, right? And your surface area is going to change. Remember, our current is going to be related to surface area. So that's changing over time. And then all of a sudden it's going to bloop, drop off. And when it drops off, it breaks that electrical connection. And so we see a drop, right? And we see a decrease in our observed current, and then the ball starts to grow again, and it drops, and it goes again, it drops. So we're going to see a bunch of wiggly lines in our experiment. So polarography, voltammetry connected with the mercury dropping electrode. This electrode gives a nice reproducible current potential behavior because a fresh drop is used for each experiment. So one of the things that you have to do in regular voltammetry is you got to polish up these electrodes, right? And you can get stuff stuck on the electrodes, and the electrode surface can get all kind of gunked up. So you're like, well, how do I get rid of that? Well, this is one way to overcome that, is to use this mercury drop, which gives you a nice fresh surface each time. So that's a pro, right? It's useful for reductions because the high overpotential for H+ reduction on mercury prevents interference by H+ reduction. Right? So platinum, right, it's good catalytic surface for reduction of H+. So whereas mercury is not a catalytic surface for that. So you've got to apply more oomph to get you into the problem of water electrolysis. Mercury is too easily oxidized to be useful for oxidizing many analytes. So the con for that is that on the other side of it, it's easy to oxidize the mercury. I mean, if you don't want to do something with something in your solution where you're going to put, like, you wouldn't want to do it in like hydrogen peroxide or something, right? Because that's going to coat the surface of that drop of mercury with a layer of mercuric oxide pretty easily. Same thing will happen with relatively high sulfur concentration solutions, where you sometimes end up forming like a calomel crust on the surface of your mercury electrode. But you can do oxidations with platinum or gold electrodes. Carbon electrodes and diamond and graphene are useful for a range of oxidations too. So here is a schematic for what this guy looks like. Right? You have a mercury drop dispenser. It says electronically controlled, and I did not have one of those. So it was just, you set up some mercury and you control that little flow rate of it dropping down. You need a little pool of mercury down at the bottom. a little drop of mercury over here. Right? You've got a auxiliary electrode. So remember, we're going to measure the current between these guys. And we got a reference electrode. So we'll apply a potential between these systematically and vary it. And then we've got a in and out thing for some gas. Okay. So the dispenser drops 1 drop of mercury from the bottom of the capillary. After the current and voltage are measured, the drop is either mechanically dislodged or basically it just falls to the bottom. A fresh drop forms. The next measurement is made. A polarographic wave can result, for example, from the reduction of cadmium 2+ to form an amalgam. So you're going from cadmium 2+ and an electron to forming cadmium dissolved in that mercury. And the half-wave potential is characteristic for a particular analyte and particular medium and can be used for qualitative analysis. So what do I have? So this is what one of those, this is what one of those polarograms looks like. So we've got kind of a jaggedy looking line, right? It's going to look, this looks very similar to the single sweep voltammogram. Okay, so remember when we started this off last lecture, we were like, okay, well, what if I just systematically vary my voltage? That's basically what you're doing here, is you are looking at a single sweep voltammogram, but it's got a bunch of jaggedy lines on top of it. And the jaggedy lines are coming from the fact that that mercury is growing, right? So you got a mercury drop that is growing and getting bigger and bigger and bigger, increasing its surface area, and then it's going to drop off. It's literally going to fall off, and then you've got just a tiny little drop that's formed there in its place. And so each one of these little spike represents a drop falling off. Okay? Layout looks pretty similar. You've got an E1/2 that's going to occur in the middle here. All right, so you've got your E1/2 half. Oops. You've got an E1/2. Right. You've got an I1/2. You got your current that occurs at the half-wave potential. And then rather than having a limiting current just be nice and smooth like it was in our regular half-wave, we've got a maximum and then we've got an average, right? And so we're just going to look at the average. And this is we're going to call it diffusion current instead of limiting current. So diffusion current takes the place of limiting current. The polarographic diffusion current is described by using what's called the Ilkovic equation. So where does this line happen? Right. So where is this guy going to happen? Our I average. Right. This is, and our ID is going to be described by this equation. So you got 708 times n d to the 1/2, m to the 2/3, g to the 1/6, and like the concentration. All right, so this is your diffusion coefficient. This is going to be your drop rate. T is going to be a function of time, and C is the concentration. All right, so as your thing is dropping, right, your surface area is going to change over time. It's going to depend on the concentration of your analyte. It's going to depend on how many electrons are involved, and it's going to depend on the diffusion coefficient. The main things that are important in this one is you're going to get information out about concentration if you need that, and then it's an easier way to get at your diffusion coefficient. So if I asked you something like this on a test or a quiz, it would be, here is this equation, right? And maybe find the diffusion coefficient if you know the concentration and M and T, right? And Imax. So, potential question might be for this, given that, and then you like look out and you're like, okay, well, here's my diffusion coefficient. My diffusion is about 13, so I got 13 in here. And if you're given D and, or if you're given M and T and C, find D. So, it would be one equation, one unknown type of manipulation. Right. So your polarography experiments look like a very noisy single sweep voltammogram. You got a very low current with a low concentration, and you don't do any stirring, and you work with a dangerous and tricky electrode. So it's very, very similar to single sweep, only your concentrations are lower, but it comes at a cost of working with a difficult electrode and working with very, very low amps. So why in the world would you ever want to do this? Right? We will talk about that in about 3 slides. So the pulse sequence that you apply is not necessarily going to be up and then back down again. What you're going to do is you're going to do a pulse on top of a linear scan. So you're going to jump this up and then drop it back down, and jump it up and drop it back down. And what you can do is you can record the difference in the current per potential pulse, right, as a difference in current. Right? And so if you sync up your differential pulses with your drops, then you can basically integrate that polarogram. So if you look at, here's a normal polarogram, right? It's got all kinds of noise on it because of those drops, and it's not really noise because it's predictable. And then you got this kind of sweep happening. If you do it in a differential pulse, you're going to end up with a peak, right? Because remember, we integrated our curves for the titration. So when we did our regular old acid-based titration, we integrated the curve. We ended up with taking our sigmoidal shape and getting a spike where our equivalence points were. So here you've still got, and you can kind of see where in this, if you look at the average of these guys, you've still got some peaks going on, right? So like right around here, right, there would be like what would look like an inflection point. And so you've got these changes that then show up, right? And so rather than integrating these things mathematically by syncing up your drop rate and your differential pulse, you're doing that integration kind of mechanically instead. And what you end up with is this peak, right? And the point on this peak is going to be related to E1 half, right? With an adjustment for whatever your reference is. The height of that peak is going to be proportional to how quickly this changes, right? And how quickly this, right? So if I went like this, right, and I had a higher concentration, right, I would end up with a bigger peak, right? And so the height of this peak is going to give you concentration information. The position of that peak is going to tell you qualitative information. What do you have? And the reason why you'd want to do this is that you can do this at very, very, very low concentrations. So this is why it is something that they will still use in pharmaceutical research, because you're dealing with very low concentrations of drug molecules. And because this is happening at a particular potential, you can do this experiment in fairly complex matrices like blood plasma without having interferences from other species. So because your E1 half is going to be unique to the molecule you're looking at, or at least pretty differentiable from other ones, and because your polarography lets you get down to really, really low concentrations, it can sometimes be a suitable technique for looking at those hard to see drug molecules that are floating around in with a bunch of other stuff. Right, so it's not completely useless, it's just a gigantic pain in the ass. Right? So our sampled current polarography, the potentiostat systematically increases the voltage, right? Whereas our square wave polarography, it just adds a square wave onto that. Our staircase profile used in the sample current polarography, it's scanned towards more negative values as the experiment progresses. And you can look at the charging current and the faradic current. And sampled current voltammetry uses a staircase voltage profile to reduce the contribution of our charging current relative to the desired measurement of the faradic current. So the second after each voltage step, the charging current is nearly zero, but there's still a little bit of faradic current from the redox reaction. And so all you're doing is you're looking at, okay, well, I'm gonna do a little stair step and what's happening here at these little corners. The analytical ferritic current, also called the diffusion current, arises due to the reduction or oxidation of the analyte on the working electrode. And the analytical ferritic current is the current we seek to measure in our voltammetry. We have this residual current that's due to the oxidation reduction of species in solution other than the analyte. So that's kind of our chemical interference. Our charging current comes from the flow of ions towards the electrode surface, because remember, we've got to maintain charge balance. Right? Because it's not from redox reactions, it's going to be an interference as well. So for us to do quantitative work with this, the limiting current should be controlled by the rate at which the analyte can diffuse to the electrode. So we use our unstirred solution. We usually do this in high supporting electrolytes, so something like hydrochloric acid, to minimize migration or electrostatic attraction of the analyte. So we don't want things going to our electrode surface that are not the thing we are looking at. We end up with a half-wave potential, which is characteristic for any analyte. And it can be used for analyte identification. Our diffusion current, that's the plateau region, is proportional to the concentration of the analyte. So how high up this goes, right? So if you have more stuff, it's going to go up higher. And that's the diffusion current, which we're going to measure that between our control, so HCl, and our solution with the analyte in it. Right. Oxygen is kind of a pain for this kind of experiment because it interferes with the reduction experiments. It's going to give you two polarographic waves when it's reduced to H2O2 and then back to H2O. So you're ending up with like a little interferent here that's got a little double wave in it. So that's why you're going to bubble in some N2 gas to kind of get rid of the oxygen. So you end up with what's called an electric double layer forming. So at the negatively charged electrode, the surface of the polarography experiment, the charged surface of the electrode attracts ions of the opposite charge, giving you what's called this double layer. So you're going to have an inner layer. So you've got your electrode surface, right? And then you've got a tightly absorbed inner layer, right? That's where all of the actual action can happen. Sometimes it's called a compact, a Helmholtz, or a Stern layer. And these are things that are tightly absorbed molecules, and it's got excess cations that help to partly balance out the electrode charge. And then you've got a diffuse layer, which is part of the double layer, right? And it's also going to contain excess cations, and that's going to give you the rest of your charge balance. Okay. In square wave polarography, you're going to get some extra sensitivity, and you end up with a derivative peak shape. So with each cathodic pulse, there's a rush of analyte to be reduced at the electrode surface, and during that anodic pulse, the reduced analyte is reoxidized. And the polarigram then is the difference between, that's why it's called a differential pulse, between the cathodic and the anodic currents. So this permits fast real-time measurements not possible with other electroanalytical methods. So yeah, it's pretty sensitive too. So there are some advantages to doing polarography. I just don't like doing it. There are some advantages of square wave voltammetry relative to the sample's current voltammetry. So you get a little bit more signal out. You get better resolution of neighboring signals, and it's a little bit faster measurement. So this is that cadmium pulse, cadmium again, but now if we do it in differential pulse or square wave, we're going to see a little peak, right, versus just a little sigmoidal shaped curve instead. So something I wanted to say about that, I completely forgot. Square wave voltammetry on an anodized graphene electrode can give you a voltammogram which the 4 nucleotides of DNA bases and a double-stranded DNA are fully resolved. So you can actually kind of separate out the reduction of G, T, A, and C. You can use an aptamer. Right? So this is an aptamer used biosensor for square wave voltammetry. So when you get drugs, they're metabolized at different rates in different people. So if I take aspirin, it's going to go through my body differently than it would through somebody else's. Ideally, this would inform how much you need to give an individual. So they have developed an Aptamer biosensor that's going to work on this differential or square wave voltammetry to rapidly measure the concentration of doxorubicin in somebody's blood. So information provided by the biosensor lets physicians provide each patient with a personalized schedule for their drugs. So if they see that you're coming through and this is getting eliminated really rapidly, then they can up the dosage. If it's hanging around in your body longer doing its job and you're not getting rid of it, then they can slow it down. So it's personalizing that medicine approach. Now, would that work? Would that be reasonable to do with something like aspirin? No. But if you're talking about like a chemo drug where you really want to give the patient the most effective treatment and balance out, well, we don't want to give them too much because it's literally killing them, or we don't want to give them too little because too little would literally kill them. And you want to keep it at just right. You don't want to use a one-size-fits-all approach and go, yeah, there's going to be a little bit of error, right? You want it to be maximized in terms of the efficacy, which means that you want to sync up that dosing rate with the body's ability to process something. So the heart of that sensor is a DNA aptamer, so they're just taking a single strand of DNA. It's got a particular sequence. It's that DNA, single strand of DNA, wants to engage in some hydrogen bonding. It can fold in on itself, and then it can also hydrogen bond to this doxorubicin analyte molecule. So you got this aptamer, it's stuck on a gold electrode surface, and the rate of the electron transfer from the electrode to methylene blue, which is stuck at the far end of this DNA, is monitored by square wave voltammetry. So what happens is, here is your analyte. The DNA kind of wraps itself around the analyte. When it does that, there's this methylene blue molecule that is now close to the surface of this gold. We can undergo electrochemistry on our reporter molecule. Right? So our electrochemistry happens with our reporter molecule, and that's going to be related to whether or not this doxorubicin molecule has bound to the DNA or not. So DNA is really useful stuff. You could do this with you could do like a protein or a peptide that would bind. Just DNA is a little bit easier to work with sometimes. So the concentration is determined from the measured current. What is kind of cool about this is that it is actually a molecule that undergoes a color change. So you could, in theory, do this optically as well. Stripping analysis is kind of the analytical scale version of gravimetry. So stripping is the most sensitive voltammetric technique because the analyte is concentrated from a dilute solution. So you got a couple of steps. Step one is reduction. You concentrate the analyte onto an electrode by reduction. And then step two, you're going to oxidize. So you're going to oxidize the analyte by scanning to a more positive potential. So basically you got this electrode that's in there, right? Sitting in there. And you're like, okay, I got this big solution with lots of stuff in it, and you're going to apply a potential so that your stuff sticks to the electrode, right? And so if it was floating around, eventually it'll make its way to that electrode surface, and then you've reduced it, and it's going to be on there. Then you basically say, okay, everybody get out. Everybody leave my party. I'm kicking you out. And depending on how motivated they are, and depending on what potential you put them at, different things are going to oxidize at different potentials. So the longer the period of concentration, the more sensitive your analysis is, right? So if you just let that sit there for like a couple of hours, right, you're going to probably capture all of the stuff in solution. Okay? Only a fraction of the analyte from the solution is deposited, so the deposition must be done for a reproducible time, such as 5 minutes with reproducible stirring, right? So you want to make sure that the conditions are all the same, right? So here is an example where you've got anodic stripping voltammogram of honey dissolved in water, and then I acidified to a pH of 1.2. And this is obtained with a 5-minute reduction step. And I've concentrated cadmium, lead, and copper onto a mercury electrode prior to recording the voltammogram. So what they done did was this. They got themselves some honey and then they dissolved it. All right, so what they've done is they have taken the electrode, they've dissolved their analyte, they're basically reducing the stuff that would be in there that's going to be lead, mercury, and copper, and they're concentrating that on the electrode surface. And so they're kind of doing an electrochemical separation almost, where you're basically sucking in all the analyte, but you got to do it in a reproducible manner, right? So you got to do it for the same amount of time for each experiment. They're doing 5 minutes. So they're concentrating your cadmium and lead and copper onto the electrode, and then they're going to go through and do their oxidation step. So this green line here is showing peaks that show up for that stripping profile, and then it is in comparison with the regular old ordinary Voltammogram down here at the bottom. And if you look right around the cadmium, you can kind of see a little bit of a bump maybe, and then the same thing over here for this copper. You can kind of see a little bit of a bump over there, right? But that concentration step drastically improves the sensitivity because you're literally increasing the amount of analyte you've got on your electrode surface, and then you're doing that differential pulse type of thing that you saw before. So your detection limits are pretty darn low. So you can strip out silver and down to 10 to the minus 12 molar. You can do a hormone and do that at times 10 to the minus 10. So you're looking at a very, very sensitive technique that works at very, very low concentrations. The detection limit of iron 3+ in seawater can be reduced to 5 times 10 to the minus 12 by catalytic stripping. So here you've got some cathodic stripping. So this catalytic stripping method example, bromate is going to convert your iron 2+ back into Fe3 before it's going to wander too far from the electrode, which enables you to have each iron 3+ measured repeatedly, right? So you're basically sticking the thing in, and it's like, oh, I'm an iron 3+, and then you convert it to iron 2+, and then bromine comes along, it's like, no, you're not, you're iron 3+ again, and it like knocks it back in, right? So this is like kind of playing racquetball with this molecule, right? Because it's like, oh, wait, I hit the ball, boom, it bounces back. Oh, wait, no, I put it, boom, it bounces back. And so you're basically going to recycle and regenerate that. You can do femtomolar DNA analysis. So DNA, you amplify that for analysis using PCR. DNA is labeled at one end with a molecule of biotin, a solution of streptavidin, that's an antibody that's going to attack biotin, coated with lead sulfide nanoparticles was prepared, and the synthetic DNA with a sequence complementary to the target is immobilized on a micro well. And so you got a little well, and you got some captured DNA. You're going to add target DNA with biotin at the end of the chain. So here you've got some DNA, right? This has the complement to the DNA sequence you're looking at. And then it's got this little biotin molecule on it. You're then going to put in a streptavidin, right, which is going to bind to the biotin. So you will see this biotin streptavidin a lot because it's like Legos when you're starting to talk about building things with molecules and proteins and doing nanotech stuff. So you will oftentimes see biotin, either biotin avidin or biotin streptavidin interactions where you want to stick two things together. You stick a biotin on one, you stick a avidin on the other, and then they've got a really high binding coefficient that's very specific. Streptavidin is just avidin that comes from Streptomyces. So you've got a single strand, right? Builds a complement target, throw in this streptavidin that's got a lead sulfide in it. You dissolve the lead, and now in your little microwell, you've got lead 2+. Right? Now you can detect the lead 2+, whereas it would be very, very hard to just detect the avidin. You can use stripping analysis for chlorate. So your peak current, which is above your substantial background current, is observed when the stripping is done with the linear function of chlorate in drinking water. The detection limit of 0.2 nanomolars or 0.2 ppb is suitable for water quality monitoring. So here they're looking at a stripping of perchlorate on a rotating gold electrode with thin layers of polyoctyl thiophene and polyvinyl chloride. So here you've got your PVC membrane, right? That's basically allowing selective permeation of your chlorate. And then you're looking at how is this interacting with that thiophene. So microelectrodes, these are if you want to stick something into a rat's brain and figure out what's going on. You can stick it into a human brain too. They're really, 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 really small. So you make these by basically taking a capillary tube and heating it and going whoop and stretching it. You can put that into a micro pipette puller or a pipette puller, and a pipette puller is just a mechanical tool that will heat and pull for you, so you get a little more reproducible results. The electrode surface, right? So if you're looking at something that's 1 micron, right? So a red blood cell is 10 microns, so this is like a fraction of a red blood cell. That's 1, 2, 3, 4. That would be the size of the entire screen, right? You're looking at just this tiny, tiny little area. If all of our currents are going to be related to the area, so we saw all of those things had some sort of term that involved area in it, right? Concentration, area, diffusion rate. Well, area here is teeny tiny, which means that the current is going to be small. The plus is that you can stick them into small places, right? And you've got a relatively low current. So you can use them in resistive media or in non-aqueous media. So you can kind of turn that into an advantage in some ways. You're also going to have a very low capacitance. We didn't talk too much about capacitance, but it's reducing the charging current and it lets you scan that voltage really quickly. So capacitance is coming from when you start putting charge onto things, it's going to act like a capacitor. It's going to kind of store that charge a little bit, and then it's going to create a mirror charge on the other side, and you can kind of reduce that because that's such a teeny tiny area. So if you look at the formula for how an actual capacitor works, you know, that's going to be related to the surface area as well. So by having a teeny tiny area, you're reducing the fact that that guy's going to act like a capacitor. If you do a cyclic Voltammogram on a microelectrode, you can reach a steady state diffusion current without going through peak current, because radial diffusion of the analyte from a hemispheric volume keeps up with the rate of electrode reaction. So in our big electrodes, right, we had like, here's our electrode, right? We've got this bulk region out here, right? So this is our bulk, right? Our bulk solution, and the molecules are just happy being by themselves. And then they have to diffuse in, right? And we have that diffusion layer, right? And before they could reach the electrode surface, right? Here, where we've got the microelectrode, right? It's not going to act like a plane. It's going to act like a sphere. And so rather than having things all come at you from one direction, they're coming at you from all directions. And so the rate of flux, the flow rate of molecules towards that microelectrode surface means that you've always got somebody coming at you, right? Whereas here, you've presented a united front. I don't know, I think I should draw from like, you know, right, here we go. These guys are like some Spartans, right? Whereas these guys are like a big Greek phalanx or something. So these are able to constantly have new stuff at their surface, right? And so you're going to reach that steady state diffusion current without going through a peak and then depleting it, because new stuff can always get there, right? So remember, we had this guy and in our duck, right, in our duck-shaped Voltammogram, right? It went up and then it reached a peak and then you ran out of stuff, right? And then it kind of decreased, right? A current decreased until we reached our switching voltage. So, but it looks like a pelican, not a duck. All right. I don't even, what sound does a pelican make? I don't know. I'm not around enough pelicans, I guess, and not quack. So So yeah, this guy, right, you see this curve in here because you run out of room, right? You run out of stuff at that surface. In our microelectrodes, right, we don't have the corresponding duct curve on the duct's head because you don't run out of stuff. So advantages, you can stick them into small places. They're useful in resistive non-aqueous media because you've got very small ohmic losses. You can do rapid voltage scans, right? Because you got a very small double layer capacitance. So you can really crank that up and down fast, which, remember, if your current is proportional to a lot of things, one of those things it was proportional to was that sweep rate. And because you don't have a lot of capacitance, you can really switch that sweep rate up faster. So you can detect very low concentrations. Detection limits with microelectrodes are increased by orders of magnitude because you don't have as much charging current. So here is one where they're doing a Voltammogram of a gold cluster. So it's 147 atoms of gold. It's got this thiol with a greasy side chain on it. That's going to let your gold nanoparticles or gold clusters be suspended in a non-aqueous solution. So they're capped with 50 hexane thiol molecules. Any of your thiol molecules smell like absolute butt. What is it? Or captane, I think, is the compound in skunk smell. So these all smell like, if you're dealing with one of them that smells like rotten eggs, you got a good smelling one. You've got so for this one, they're looking at a 25 micrometer diameter platinum working electrode. And your nanoparticle is going to exhibit oxidation states from -7 to +8. And so this is what we're seeing here is each step is representing an electron oxidation state change. So you're going from -6 to -7, -5 to -6, -4 to -5, and then all the way up to +7. You can use it to study brain dopamine. So dopamine is going to be electrochemically active. Right? You can sense dopamine. It's got an E1/2 to it. The electron micrograph here is a tip of a naphthalene-coated carbon fiber electrode for sensing dopamine in the brain. The inner carbon microelectrode has a diameter of 10 millimeters. I think they meant nanometers, but yeah. So you've got this naphthalene membrane. That's going to let cations through, but not the anions. So it's going to give you some selectivity at that membrane. Dopamine is a cation that moves through the membrane. It's going to be oxidized from dopamine into, I forget what it's called when it gets oxidized, to oxidized dopamine. There's a name for it. And I'm just having a brain fart. So you can study single adrenal tumor cells. So here's a microelectrode where you've got a micropipette that's delivering potassium chloride. You got a cell that's pressed up against this electrode, right? So, even though this guy's 20 microns, right, which seems really, really small, right? So there's a 10 micron thing. Our cell is even smaller. So we're not going to be able to necessarily get inside of a cell, but we can certainly smush our cell up against it. So here they're measuring up against a single cell. So you got a carbon fiber microelectrode array with 7 electrodes, 1, 2, 3, 4, 5, 6, 7. It's pressed up against a PC12 cell distorted into a crescent shape by the electrode. So the cell's kind of like, all right. The micropipette is going to deliver some KCl, potassium chloride, to stimulate dopamine release from the cell. And then you look at these amperometric traces from the electrodes during the release of that neurotransmitter. So what happens is, right, we got our cell, it's smooshed up against, the electrode. And you're going to release some KCl, right? The KCl is going to walk in towards the cell. The cell is going to go, oh, hey, it's going to release some dopamine, and then you're going to measure that dopamine response over here on the electrodes. All right, so that's the end of electrochemistry. Do you guys need a moment to process all that, or do you have any questions that you might immediately come to mind about electrochem? Okay. We have about 15 minutes left. I could either start into spectroscopy or I can leave it for next time. Who wants me to start in on spectroscopy, or does your brain need a break? Break, okay. Totally fair. The stuff with electrochem is applying all of the material that you learned in 2 chapters ago in a very specific way, and it takes a while to process. So I am fine with like letting your brains go. So I'm going to stop recording right now. We'll do next, since we haven't started the notes yet. No, I will need to move that next chapter homework. I want to make a note of that now. Move chapter 18 homework. Yeah, I mean, there's no point in giving you homework on stuff you haven't studied yet. So I will need to move the homework. And same with the other ones. So we will probably not do homework on the separation stuff. So 18 or 19 might well be our last homework. So this one or the next one is probably going to be our last homework, just because we will run out of time. So cool. All right, I'm gonna stop the screen share and I will upload these. I know some people wanted to hang out and still talk for office hours, so give me like 5 minutes to record this. Oh, I totally forgot to mention I am I am out of space on Canvas to upload these. So I'm making a YouTube channel and I'll put a link to these in the YouTube channel. So they're still recorded and I still got them. It's just that it's not going to be a file on Canvas. It will send you to an external YouTube link. Okay. All right. I'm going to stop the share in this. And I will see people who want to see me in office hours over on the office hours link. Okay. As soon as I can figure out where my button went.